Okay, so in this chapter, we're going to talk about obviously the liquid state. We're going to talk about solutions. We're going to talk about some forces that hold together one molecule with another molecule with itself, and some of the effects that it has on solutions. For example, some properties like boiling points, melting points, and so forth. So let us sort of start talking about some of these properties here. So the first sort of property we're going to talk about is one that's referred to as an intermolecular force. And intermolecular force, much like the name sort of sounds like, is basically the force that holds together two molecules. And that means it could be two of the same molecules, two of the different molecules, but it's basically the force that holds, for example, this one molecule together with this other molecule here. Um, it is really the force that's responsible for things like boiling points, melting points, freezing points, and so forth. And whether or not, these sort of properties are large numbers or small numbers. So if we just think about it sort of logically, what happens when we have an intermolecular force is, for example, if we have these guys sort of bonded together through this intermolecular force, if we started to heat it, say this is in the liquid state, and we start to apply some heat, it's going to obviously work on this force here between the two molecules. And to get us into the gas state, they obviously would have to sort of break apart from each other in that sort of sense. If the force here holding those two molecules is a really strong force, really strong intermolecular force, then we would expect the boiling point, the melting point, and those type of properties to be pretty large or high, I guess is a better way of putting that. If this force that's basically holding those two molecules together is relatively weak in terms of sort of intermolecular force, we would expect those boiling points, melting points to be relatively low. And what that means is really the way we supply heat, right, is, for example, boiling water or something like that, right? We supply energy and heat from, say, fire or flame. In certain cases, you don't have to supply a lot of heat or energy to get these guys to sort of break if they're held together by sort of weak forces. Now, what are sort of intermolecular forces and what are some of the basic sort of idea of an intermolecular force? Really, we're going to talk about several different types of intermolecular forces here, but really they all boil down to essentially this basic attraction of the positive side of one molecule being attracted to basically the negative side of another. So it's sort of that opposites attraction there that we've talked about many times, the positive negative electrostatic attraction. And pretty much that is the basis of all intermolecular forces, is there's that positive negative attraction that occurs. For example, if we had two water molecules that were hanging out, water, as we know, is a polar molecule, which means the oxygen side is more negative, the hydrogen side is more positive, which means when it gets near another water molecule, oxygen side is more negative, hydrogen side is more positive, and now we have that negative from one oxygen attracted to the positive hydrogen in another water, and that is an intermolecular force. That is the force that holds that one entire water molecule basically together with another entire water molecule. Any questions on that there? For the most part, we're actually, I'll answer your question here on the next slide. I think we'll probably answer your question if you just, let's take a look at that slide there. Um, the other type of force that, that we see and sort of talk about are ones that are basically what are referred to as intramolecular forces. So intramolecular forces, these are the forces that are within a single molecule. So for example, if we take the same water molecule, but not two of them, just one individual water molecule, the force that basically holds the oxygen to the hydrogen and the oxygen to the hydrogen on that side, those are what are referred to as intramolecular forces. We also know these as what holds the oxygen and hydrogen together is they're going to be sharing electrons, right? So there's some sharing of electrons that are happening here. That's also known as covalent bonding, right? So that covalent bonding is basically what's happening within the individual molecule, right? Between the oxygen and the hydrogen, and that's what's sort of holding that together. If you think about more of an ionic compound that we saw before, it is the sodium ions, for example, and the chloride ion. That is basically holding that together. That's that electrostatic attraction, right? And that is basically ionic bonding. So to sort of answer your question, sort of a lot of what we focus on in terms of just the bonding aspect of it, those are more intramolecular forces. Those are, again, the forces that basically holds that sort of individual molecule together. When we start talking about sort of properties like boiling points, melting points, or things like solubility and stuff like that, that is more intermolecular forces. So that's sort of the difference between those two things. Again, intramolecular forces, kind of like your bonding and stuff within just that one molecule. Intermolecular forces is sort of how a molecule sort of interacts with itself and also other different molecules. And that's where we see things like when we talked about the solubility rules and why some things are sort of soluble in each other and some things are not soluble in each other. Also, again, like we'll talk about here in some later chapters as well, the reasons why we have boiling points that are maybe higher or lower and stuff like that is those intermolecular forces. So between those two, intermolecular forces and intramolecular forces, the intermolecular forces are always much weaker than, say, your ionic bonding and your covalent bonding. They're very, very weaker than those two. The reason for that is, if we kind of go back to sort of our water example here that we were just talking about, again, that intermolecular force between the negative oxygen, the positive hydrogen, that holds that together. Now, that again is our intermolecular force. And again, here's our intramolecular force. So how do we know just a realistic example that the intermolecular force is really weaker than the intramolecular force? Well, we've all probably heated water before. And when we go to heat water, what ends up happening is, as we get to that 100 degrees Celsius, we're at the boiling point, we're transferring our liquid water into gas, right, or steam. What ends up happening is actually this bond that breaks first, right? And we know that because when that bond breaks, we then end up with individual gas molecules that have now gone, into the gas phase, right? Which is basically steam, right? These guys break off into individual gas molecules, which again, as I mentioned, is basically steam. And that's what you see when you, again, boil some water to make some pasta or something like that. What you don't see when you, for example, put your bowl of water up there on the stove and start boiling it is you don't see the formation of hydrogen gas and oxygen gas, right? And that is definitely what would happen if the intramolecular force was weaker. If the intramolecular force was weaker, what would happen is, as you start to heat, say, liquid water, the bonds between these guys would start to break. And what you would end up with is definitely not steam. You would end up with oxygen gas and hydrogen gas, which is not a very good situation probably there with the fire on. And that does not happen. So this is a very simple sort of illustration that we see the intermolecular force always weaker than the intramolecular force. And again, if it basically was the opposite way around, you would have like alphabet soup. Everybody would fall apart. All the individual parts would fall apart. But what ends up happening is, because that intermolecular force is weaker, we get that separation that occurs between the two molecules rather than the intramolecular forces, which is the individual sort of bonds that are happening. Any questions on that? That is also why, as we'll talk about, when you think about some type of ionic salt like sodium chloride, when you heat sodium chloride, if you ever have done that before, maybe in an experiment, maybe sodium chloride or salt water, when you evaporate off the water part, what ends up happening is you're left with sort of a white crystal type solid if you're dealing with sodium chloride. And if you continue to heat that solid, what will end up happening is it will actually start to melt before it will go into the gas phase. And that's because once you hit that sort of just sodium chloride by itself, you're now dealing strictly with intramolecular forces, which is a very, very, very strong attraction. And the best you could do is to get these guys to kind of start melting. They'll never really, under really normal sort of conditions of heat and stuff, they really will not just jump into the gas phase because it's a very, very strong attraction. So intramolecular forces within the molecule, always much stronger than any intermolecular force, which is the force that holds, again, two or more molecules basically together. Any questions on the differences there? Okay, so what we're going to actually focus in on is actually intermolecular forces. So we're going to talk about some different intermolecular forces that occur. So starting with this first one here, and again, just to clarify, what we're talking about from this point on are all intermolecular forces. So again, these are the forces between one molecule and another. The first type of force that we're going to talk about is one that's referred to as a dipole-dipole force or a dipole-dipole interaction. You may remember this word dipole from when we were talking about bonding. What does a dipole mean? A dipole pretty much means you got a polar molecule. So if you remember, if you just had something like HF, it is a polar molecule. It has, right, a dipole moment, and hence where the name comes from. So what does that really mean in terms of how these things interact with each other? Well, if we have a polar molecule and it has a dipole moment, it means that there is one part of that molecule that is more positive than the other part is more negative, right? There's that unequal sharing of electrons as a whole. So these are things that we're talking about, maybe not diatomic, but in a three or more sort of situation, atoms, these are things where we looked at, if you remember, are there polar bonds, the molecular geometry of the molecule. So this is sort of what we're talking about. And if the answer is yes, there is a polar molecule, that's essentially what you have. And when you get basically two polar molecules together, as we can kind of see on the bottom as well, basically got a polar molecule. Again, not just a polar bond here we're talking about the entire molecule as a whole is polar. Remember, you can't have molecules that have polar bonds but actually be nonpolar. So that's an important thing to keep in mind. We're talking about here the molecular polarity of the molecule. Because there's a positive side of one and negative side of another, as I was just talking about before, that is where the intermolecular force is going to be able to basically connect with each other through that opposites attract, that positive and negative attraction. That's an intermolecular force, badly written up there on top. And that's what we see here. Again, we're going to get these guys to really line up, get all that kind of positive, negative attraction sort of happening. You might even get some, crossover sort of attraction sort of happening as well. And what they typically tend to do, especially when things sort of get into the solid phase, obviously when they're a solid phase, they're packed in really tight to each other. So they do try to, I guess wiggle around might be the wrong word there, but they do try to kind of move around enough that they really do try to maximize the attractive forces. So they kind of move a little bit and move a little bit, kind of arrange themselves where they can kind of maximize the positive side of one molecule being next to the negative side of another. And obviously they also try to minimize no matter what you do, you're going to end up with some negatives near negatives and some positive sides near positive sides, but they do sort of kind of move around a little bit and adjust enough to try to minimize that the best they can. So this type of interaction, dipole-dipole forces, is the main type of intermolecular force when we're dealing with basically polar molecules and polar molecules. So basically two polar molecules together. Now, mind you, this could be two of the same polar molecules, like, perhaps like water is not really the great example here, but, two polar molecules with itself are two different polar molecules interacting like this. This is basically the main force that they will use. And that's what we see here sort of in this picture. Again, when you get a whole bunch of them together over here, they do, again, try to rotate to really sort of highlight those areas where we could get that positive and negative attraction. And again, sort of minimize those areas. As you can see, you got some negatives and negatives near each other. You got some positives and positives near each other. So there's kind of no way around it. It is going to happen, but they really do try to keep kind of moving until they could kind of really maximize that positive negative attraction. Another type of intermolecular force, which is kind of similar to dipole-dipole, this is one that's specifically referred to as ion-dipole interaction or ion-dipole force. And it is pretty much what it sounds like. It is a force between an ion and a dipole force. So what does that mean? It means pretty much you got either a cation, which is going to be positively charged. You also have a polar molecule, which again will have a negative and positive sort of charge here. And again, that is going to give them a way to interact with each other, right? Same thing would happen if you had an anion, right? Which would be negative. It also would be attracted to the polar molecule, but it actually would be attracted to the polar molecule in sort of the opposite direction. The negative side would be attracted to the positive side of that polar molecule. That essentially gives you that interaction that you're looking for, that positive and negative interaction. That's exactly right. That's actually exactly what I was just about to talk about. This is exactly the interaction that occurs when you take an ionic compound like sodium chloride and you do put it in water. This is pretty much that attraction. And what ends up happening, when the sodium chloride goes in for a swim, it's basically positively charged ion, and we get the chloride ion that's negatively charged. And as we just talked about, water is essentially polar, which means it does have, again, that negative side and that positive side. So what happens with our sodium ion is the negative side of water, which is the oxygen, will start to basically surround the positive ion here. Now, the negative ion, like the chloride, will actually be surrounded by water, but it would be surrounded by water through the hydrogen in this case, as hydrogen is more positive. And this does two things, as your question sort of said. It does actually, this is pretty much how things dissolve. We sometimes think about things dissolving and sort of quote unquote disappearing, it's gone, but it's really not gone. They just basically get gobbled up by all these waters and it gets mixed into all these water sort of networks and you no longer can see it anymore. It's kind of hidden within all the lots and lots of water molecules that are there. So it appears like it's gone, but we definitely know it's not gone. Again, if you've done something like what I was just describing earlier, we take some sodium chloride solution or saltwater solution and you heat it up. When all the water evaporates, your solid returns. And that's because when all your water evaporates, all these waters basically go away. And there's nothing left to prevent the sodium ion. So if you evaporated off all the water, so if you like heated this thing, add a little heat, what would happen is all that water would evaporate off. And now definitely these guys are going to come back together because there's nobody in their way. And they're going to reform that solid sodium chloride. So if you've ever done that, again, you get that little, I'll draw it red, but it's usually a sodium chloride, a kind of a white solid residue that's left over after all the water basically evaporates. And that's essentially what's happening when we dissolve something. That's why ionic compounds, for the most part, are pretty soluble in water. They're very, very soluble in water because of this sort of interaction. And it's basically an ion dipole interaction that's occurring. We speed this along sometimes, right? When we have a solid, if you have a solid in water, you typically will speed it along by stirring it, right? When you're stirring it, you're adding energy. In addition, you're throwing a bunch of waters all over those ions, right? And it's allowing them basically to start plucking those ions off and allowing the solid basically to dissolve in that particular case. Any questions on that there? And that's why, as we will talk about here in just a second, that's also why when you kind of take something that's ionic and you try to dissolve it, for example, in a nonpolar solvent, it doesn't work very well. And that's because, if you remember, a nonpolar guy basically is sharing electrons equally. It's essentially no charge, which means when you get your ions floating around there, they're like, I'm not really attracted to you. There's like no charge. There's nothing happening here. So they really don't mix very well. So that's why when we talk about solubility, we'll probably talk about a little bit later on in another chapter, I think, as well. But there's a very common sort of saying that's sort of said about solubility, and it's the idea of like dissolves like. So things that are similar in terms of their intermolecular forces allows them to interact with each other and also, again, basically dissolve in one another. So ion dipole is pretty much like the name implies. It's pretty much the force that's used between an ion and a polar molecule. It is sort of under the umbrella of dipole-dipole sort of interaction. So what happens with our nonpolar guys? Let's talk about sort of how they typically can interact with one another, and a couple of different ways we could get sort of these guys to interact with each other. But dispersion forces, these are essentially the forces that hold nonpolar guys with nonpolar guys. So these are the forces that hold basically a nonpolar molecule together with another nonpolar molecule. This, out of all of these intermolecular forces, as we will talk about, the dispersion forces are pretty much the weakest. So it is the weakest in terms of interactions or intermolecular forces. And there's a couple different ways we could kind of get dispersion forces to sort of occur. One way is we could kind of induce a dispersion force to occur. And what that means is they're the weakest because these are kind of what are referred to as temporary type of forces that interact with each other. How can we induce sort of a dipole to occur? A dipole, again, is just that sort of separation of charge. You could imagine if you had, like we have sort of at the bottom, a neutral guy just kind of sitting there, and you did put something with a positive charge next to it. What's going to happen with our neutral guy is the electrons here are going to go, well, there's positive over there, kind of attracted. So they probably are going to move towards this side of that neutral molecule, which ends up making that neutral molecule sort of temporarily gaining a negative charge on the left-hand side of my example and have a positive charge on the right-hand side of my example. And that's really good because now these two guys have a way to interact with each other. And what I just described here is what is sometimes referred to as ion induced dipole. Is kind of this temporary, all right, we'll have a little attractive force there between it. Electrons decide kind of to go back, ion decides kind of to go away a little bit. Everything's going to kind of break apart. So it's really sort of a temporary sort of attraction that occurs. Also, same thing with dipole induced dipole. The only difference is instead of taking like an ion next to a polar molecule, we take a polar molecule next to a neutral guy. And in my example here, negative side's here, which means actually the electrons in this guy will decide to go this way. And that's going to create our polar molecule that we had. And this guy that normally does not have a charge will temporarily gain a negative and positive charge, again, able to provide some interaction. This also explains why sometimes, when you think about things that, for example, don't mix, like oil and vinegar salad dressing, for example, right? And for a moment, right, you could shake it up and things seem to mix and things seem to be all mixed in and everything like that. You pour it on your salad, you're really happy, right? And that's because honestly, everything can do some type of dispersion forces like this. We could induce some type of interaction that could occur. But just like the salad dressing example, if you take the bottle of salad dressing and put it back on the table, at some point, what you're going to see is everybody kind of separate out from each other, right? The oil and the sort of vinegar part will sort of separate out from one another. And that's because these type of interactions that they can do is really temporary interactions. They have no real long range way of interacting with each other over a long period of time. And that's why, again, they're really the weakest. That's why everything technically can do some type of dispersion forces. There's some type of interaction that can occur, but they can't really maintain that interaction. And that's really different than earlier here when we were talking about, say, our dipole or ion dipole. These guys here, when we're dealing with dipole like we were talking about earlier, and you have a polar molecule, no matter what the situation is, this polar molecule is always going to be polar. It always has a positive side and negative side. It doesn't have to wait for some situation to occur for it to gain that positive charge. It's not going to lose that positive or negative charge. The electrons aren't going to decide in that polar molecule, I don't want to be polar anymore. Let's go share everything equally. So they have sort of this fixed positive, negative side when we're dealing with a polar molecule. And that's why dipole is a relatively strong intermolecular force, because no matter what the situation is, it's kind of good to go in terms of positive, negative attraction. Even our ion and dipole, good to go. Ions are always going to have charges, right? And dipole guys, again, polar molecules, always going to have those charges no matter what. But here, when we're getting with something that normally doesn't have a charge, we sort of has to make it get a charge. It's just, and it's temporarily and based on the situation. That's again why these are temporary and sort of very weak, because they need something to kind of occur to allow them to interact with one another. So this is one way that we could kind of get a dispersion force. We could kind of induce it by putting something that's positively charged. But what happens in sort of the case of, we get these two nonpolar guys together, they really don't necessarily have a charge ever per se, kind of normally speaking. But there is a way that sometimes what occurs is the ability of a molecule to create what is sometimes referred to as an instantaneous dipole. And what does that really mean? Well, it really means that if you have, for example, two nonpolar molecules near each other, they obviously are nonpolar, which means they both are essentially neutral. There's no positive side or negative side. But electrons, right, are sort of constantly moving around, right? So they're constantly kind of flying around and stuff like that. So it is possible that at some point along the way, all these electrons, say in this first nonpolar molecule, decide, hey, let's just all go take a vacation over here on this side of the molecule. And what's going to happen in that situation is if all the electrons, and we'll call them nonpolar A, nonpolar B, in molecule nonpolar A decide to go to the right in this situation, this guy that normally does not have a charge will again temporarily get a charge. And if he's still sitting next to the other guy that's nonpolar, we're going to get some interactions here where the electrons and this guy go, no thanks, that's negative. I'm going to go this way. And now nonpolar molecule B, which normally doesn't have a charge, will now temporarily gain a charge. And now if we kind of look at the situation, these two nonpolar molecules, which normally are sharing these electrons equally, have now temporarily gained charges. And now we have a way for those guys to really interact with one another. And the ease or ability at which a molecule can kind of do that is what is our kind of have those electrons kind of move one way or the other is what is known as polarizability. So the greater the polarizability, the easier at which those electrons can kind of be distorted. You know, everybody kind of moving their electrons around in this sort of situation. Typically, this occurs with the larger number of electrons, the greater the polarizability. Why would that be? Well, more electrons means further away from the nucleus, and also a lot more electrons moving around and a lot more places for this to occur. And we get these sort of easier sort of polarizability that occurs. Any questions on that? So instantaneous dipoles is really the, which is really falls under, again, dispersion forces, is really, again, the intermolecular force that nonpolar molecules basically use with other nonpolar molecules. Any questions on that there? Yeah, so to sort of answer your question, it does sort of, they sort of, interaction here, then kind of next interaction. Some stay a little bit longer than others, some are a little bit stronger. But yeah, it sort of is within two nonpolar molecules, it's sort of constantly occurring. So if you think about it, right, we're not really in most cases talking about sort of two isolated, just two individual nonpolar molecules. So if you have like a beaker where you dump sort of the nonpolar um, A in there and you dumped nonpolar B in there, you got lots and lots and lots of these molecules, right, all floating around. So it's sort of consistently sort of happening. And you can kind of think of it as it happens here. Maybe then moves to the guy next to it, and then maybe he forms some new interactions with ones next to it. So it's sort of a constantly occurring thing that you wouldn't be able to sort of visually kind of see, oh, there's a lot of interaction sort of happening. It would look like really nothing happens. For example, if you took two nonpolar guys and you threw them into the same test tube, it will just look like one solution basically, because everything will mix, everything will be soluble in each other. But underneath the surface, you got all these sort of dispersion forces happening, and it does sort of happen relatively quick in that sense that, it's not just an isolation between two guys, but a whole bunch of molecules are obviously floating around there, and this is sort of constantly occurring and stuff like that. Other questions? So just to also talk about sort of the strength of these forces, especially dispersion forces, we typically see a stronger dispersion force as the molecular mass increases or molar mass of the molecule increases. So for example, if we had, say, this guy here, by the way, And by the way, when you look at this is all carbons and hydrogens, which is nonpolar bond. This is carbons to carbons, which is nonpolar. This guy is going dispersion forces basically all day and how it interacts. Take the same sort of elements and, you had, say, this guy and continue on. And again, these are all sort of hydrogens. I won't draw them all, but hydrogens all the way across on both sides, all the way around, basically. But the difference between this guy also would be obviously using dispersion forces. But definitely the guy on the right, if we want to know, for example, remember these intermolecular forces are what basically dictates, how big or large the boiling point is or melting point. We would expect actually the boiling point, melting points to be larger in this guy because he definitely has a lot more, obviously, atoms. A lot more atoms means a lot more electrons. A lot more electrons. There's probably that greater ease at which these electrons will kind of move one way or the other, right? There's just so many electrons versus this guy. We would expect a lower sort of boiling point or melting point because of that. It has a lot less electrons when comparison. So even within sort of dispersion forces, and you're trying to maybe compare, the boiling point or melting point of a nonpolar molecule with another nonpolar molecule, the size of it actually matters in this case as well. Any questions on that there? Now, when we talk about dipole interaction, dipole induced dipole, and dispersion forces, these are again sometimes what is referred to as van der Waals forces. You remember van der Waals, he was the guy with the scary ideal gas law equation, right? That had all those correction values. And what did he have correction values for? How those gases interacted with each other, essentially, right? And he did obviously a lot of work with sort of intermolecular forces. And again, they're sometimes referred to as van der Waals forces. Here's maybe a prettier picture of what I drew, but same idea here. Again, atom A is normally a nonpolar guy, so is B. At some point, the electrons basically shift one way or the other as they're constantly kind of moving and creates a temporary charge here. Now we have a positive side. This is a partially positive charge, partially negative charge here between these guys that normally don't have charges. And again, temporarily, they have a way to interact with one another. The last type of sort of intermolecular force that we're going to talk about is one that's a relatively strong intermolecular force, and that is what is known as hydrogen bonding. Hydrogen bonding is actually also really a dipole-dipole interaction. But it's a special type of case of dipole-dipole interaction, and it's relatively strong for sure. Out of all the sort of intermolecular forces, this type of interaction is actually the strongest. And it is pretty much what it sounds like. It is a bond between hydrogen and a nitrogen, oxygen, or fluorine. So it is really a bond between hydrogen, and there needs to be a nitrogen, oxygen, or fluorine involved. Why are those three elements sort of importance? Well, if we look on our periodic table there for nitrogen, oxygen, and fluorine, it's right there on top right. And if we think about our good friend fluorine, that is the most electronegative, right? And if you think about electronegativity, that's really what kind of determines the separation of charge. So we get these hydrogens as attached to this really electronegative atoms, either nitrogen, oxygen, or fluorine, that has to be there and involved. We end up getting basically a bond with hydrogen in one of those elements where hydrogen will end up being more positive. The other element will end up being more negative. And that's going to allow us to see hydrogen bonding basically take place. If we have the hydrogen and nitrogen, obviously this guy's going to be more negative. This guy's going to be more positive. Hydrogen and oxygen, same deal. Hydrogen and what I missed there, fluorine as well. So again, all those guys have the ability to hydrogen bond. And as we saw at the very beginning here, that is essentially really what we're dealing with water when it sort of hydrogen bonds with itself or other things. Again, here we see really what we need for hydrogen bonding to occur. I have a hydrogen that's bound to an oxygen, so we can definitely have hydrogen bonding. Same thing on this water, obviously, same situation. And again, our sort of opposite attraction there, oxygen in one to the hydrogen in the other, allowing hydrogen bonding basically to occur. Question on that. So if we think sort of about, can we hydrogen bond with hydrogen, right? So what happens if we had something like methane? And sometimes people are confused because they look at, for example, something like methane and they go, well, it would kind of make sense to me that it could hydrogen bond because, I got a lot of hydrogen sort of happening there, right? So I think it should hydrogen bond perhaps. And the answer is actually going to be no, it really cannot hydrogen bond. Even though it's got a ton of hydrogens, the problem here is first off, that hydrogen is not bound to a nitrogen, oxygen, or fluorine, which is necessary to create that separation of charge, that positive side and negative side. It's actually bound here to carbon, which is just to the left of nitrogen. And although it may not seem like a big difference there, if you remember just vaguely going through our electronegativity values, this guy is like 2.5, this guy is like 2.1. When we do our difference in electronegativity, as we've done before with this one, 2.5 minus 2.1 gives us that 0.4 difference, which is technically a nonpolar bond. So even though it's got a ton of hydrogens there, it does not have the ability to hydrogen bond. So what would this guy be doing? This guy definitely, we know now, right, that these are nonpolar bonds. This is also a symmetrical geometry, if you remember. We should know that CH4 is actually a nonpolar molecule. And because it's a nonpolar molecule, we should know that it should be using dispersion forces as its main route of interaction. And it would do really well with other nonpolar molecules that would also be using dispersion forces. This guy would do really bad with water because it has no long way range to interact really well with, say, water or something like that. Question on that. Now, let's take a look at maybe another one here. Let's say we had our good friend ammonia. Can ammonia hydrogen bond? And the answer is it has hydrogen. So again, much like the other ones, we got hydrogens. And what do we got in the center? We got nitrogen, which actually is a winner in this situation. And in this situation, the hydrogen again here would be more partially positive. Nitrogen being more electronegative would be more partially negative. So if another ammonia was around, we would get the attraction between the positive hydrogen of one and the negative of another, and it's able to hydrogen bond. By the way, also would be able to kind of hydrogen bond over here as well with water. So a reminder, it doesn't always have to be, the same molecule and the same molecule interacting. You can have different molecules that can interact. And as I mentioned a little bit earlier before, that's really why certain things are more soluble in each other. And it's because they have a way to interact well with one another, because they have very similar sort of intermolecular forces. And that is essentially what makes a lot of things, mix together. Or also, I guess, on the other hand, is why certain things don't mix very well if they don't really have ways to interact well with one another. Any questions on that there? So just to sort of summarize what we talked about, here are some hydrogen bonding action happening here. Again, negative of the oxygen, positive of the hydrogen, negative and positive of the hydrogen happening in each of these cases. How do all these sort of different forces interact with each other? So just to sort of summarize, on sort of our one end, we have really sort of hydrogen bonding. And hydrogen bonding really is between two polar molecules. And the importance of that is that they actually do have the ability to hydrogen bond. So remember, what makes it have the ability to hydrogen bond is we need a bond between hydrogen and nitrogen, oxygen, or fluorine. So it's got one of those three bonds happening. And again, a bond between hydrogen and nitrogen, oxygen, and fluorine, basically for the ability to do that. In the middle, sort of here, is dipole interaction. And here also between a polar molecule and a polar molecule. And these would be polar molecules that do not have the ability to hydrogen bond. And sort of at the other end of the extreme is our dispersion forces. And our dispersion forces are actually the ones that are the main one for nonpolar and nonpolar molecules. These again are those kind of temporary forces. So really, in terms of strength, as I kind of alluded to, over here would be the strongest in terms of strength of that bond. Over here would be the weakest in terms of the strength of that bond. And what would that affect? It would affect the boiling points and melting points. So kind of for boiling points, melting points, we would expect the higher ones to be over here. By our hydrogen bonding, we would expect the lowest to kind of be at this end of the guy. And again, as we talked about, it is those sort of, excuse me, it is the strength of that intermolecular force which affects the boiling points and melting points. Again, just logically speaking, the stronger it's held together, the more energy you got to put in there to get them to break apart. The more energy you have to put in there basically relates to a higher temperature. And that's why we see those higher boiling points and melting points. So you may be asking yourself, like, what would be a polar molecule that doesn't have the ability to hydrogen bond? So, we've seen, for example, something like NF3, for example, something like this, right? Has no hydrogen, so it can't hydrogen bond, but it is polar. So it would interact right well with dipole-dipole sort of interaction. Any questions on intermolecular forces and sort of the differences between them there? So now that we sort of have some information about how, again, one molecule sort of interacts with another molecule, we're going to talk a little bit about some properties of liquids, really, in the liquid state, and some different types of properties that we'll talk about. Obviously, you should be familiar with the liquid state. In the liquid state, we obviously have everybody near each other, but there's a little bit more room for movement. Things can sort of pass one another. This is why liquids, right, are fluid when we think about them. They are in motion. They can't really compress them. They kind of make a mess. When we talk about sort of viscosity, it's basically the resistance of a liquid to flow. And it's related to the intermolecular forces. Water has a low viscosity and motor has a high viscosity. And again, if you just sort of think about viscosity also decreases with temperature increasing as well. So, you know, water, has a low sort of viscosity. Think like motor oil, I put it in there. It's very sort of viscous as it's coming out of the sort of container. There's sort of different types of forces that we see with sort of solutions and some things that occur. So, for example, one type of force that occurs is what is known as cohesive forces. And cohesive forces are the forces of attractions between a molecule of a single substance, like the hydrogen bonding in water. So what ends up happening, for example, is, for example, this is also why we sort of see a meniscus. And when we talk about a meniscus, we see the curvature of the liquid. And that's because of actually what are referred to as adhesive forces. And adhesive forces are the forces of attraction between two different molecules. So what makes the water do the whole curvature thing when it's in a container? It's because the cohesive forces, the attractive forces between, say, water and water, which would be our cohesive forces, are actually less in this case than the attractive forces between water and the glass. So what ends up happening is, as we put a liquid into sort of a glass container, there is some attractive forces between the water and the water, but there's a stronger attractive force between the container and actually the liquid. And what ends up happening on the sides is, because of that attractive force, that adhesive force, we start to see the liquid kind of rise up on the sides of the container, creating the meniscus that we're talking about. And that's why we typically read the volume from the bottom of the meniscus, because without that force, basically this would drop back down to that level, this would drop back to that level, and that's essentially where the level or the volume of the liquid is. We just kind of see that curvature happening because of the much stronger adhesive forces versus the cohesive forces. And it's not always the case that we do see this meniscus sort of like this U shape. We'll see an example here in a bit of where it actually kind of goes in the opposite direction. Another sort of example or property of water is what is referred to as surface tension. And surface tension is basically the elastic tendency that we see basically on the surface of, say, like water or a liquid. So let's just take our sort of water molecules, if you will. We'll just kind of draw that as a water molecule. On the surface, these water molecules, draw some water molecules underneath it as well. So the water molecule sort of on the surface feels attractive forces to obviously some water molecules below it. It also feels some attractive forces from water molecules to the side of it. So what you end up having on the surface of the water with those guys is you got the guy kind of pulling down and pulling to the side, sort of extending, right, the water level there, and sort of the surface tension that's happening at the basically surface of that liquid. It sort of spreads out, if you will, right? It makes this sort of tension because he's being pulled pretty much in all directions except upwards. He's not being pulled. So because he doesn't have that upward pull, it's kind of like people stretching something left and right, and then somebody also pulling it down. You get this really tight surface that occurs as a result of that. It is higher in liquids with greater intermolecular force. This is, again, why you can kind of lay carefully a paper clip on sort of water there. Also why, sort of animals is wrong. Insects, I guess, is the one I'm trying to figure out there. Can kind of walk on the surface of water and stuff like that. Here's a much maybe a better or worse picture of what I just drew. But the difference is here again, our surface water is filling that pulling left and right, and again, sort of spreading out on the surface. And that's different than, say, a water molecule below the surface. It's sort of feeling a little bit more of equal kind of pulling and attractive forces sort of all around because it's really surrounded by other water molecules. Again, at the surface, we don't have that sort of above water molecules that really help in that sort of aspect of it and allow it to spread out. This is also, why, for example, when we kind of do something with water, for example, if we want to wash our car, um, you know, water typically will bead, for example, especially when it hits something that's like an umbrella or your car's really waxed and it rains on it, or you get water on it, you see all these little beads of water, right? Or even on an umbrella, you can sometimes see that. And water typically, because of this really strong sort of surface tension, it typically will just sort of bead on there rather than sort of spread out. So, what can we do to add to it? We could oftentimes add soap along the way here, for example, or detergent. And what is soap or detergent? Um, Michael, did you have a question or just hit that? Okay. Soap basically is a very long, basically molecule that has a lot of carbons and hydrogens. And again, I won't necessarily draw all the carbons and hydrogens out, but there's very long carbon and hydrogen, and it typically has what is referred to as a carboxylic acid type of group at the end. And this group at the end is actually polar. This sort of carbon hydrogen group, and again, hydrogens go all the way around pretty much all the carbons, is really nonpolar. And that's what's sometimes referred to, as you can see in the picture on the bottom, the nonpolar tail. And the front is sometimes referred to as the polar head of soap. And it allows soap to work really well because dirt is actually very nonpolar most of the time. So what ends up happening when you sort of use soap is the nonpolar part of soap, and I'll just draw it as a squiggly line, which is a very bad line structure. So basically the nonpolar soap will be really attracted to the dirt, as we were just talking about. They're both going to kind of use dispersion forces. They're going to basically mix really well. And what that ends up doing is creating what's referred to as a micelle at the end of this sort of situation here. And what we have on the outside of soap that has surrounded all this dirt and grime is the polar part of soap, which is really good because usually after we soap, right, we typically wash it off with water that's polar. So what ends up happening is sort of the non-polar side of soap pretty much grabs up all the dirt and grime, traps it, and then on the outside, we basically have the polar side of soap, which then when you use water is going to be very much attracted to the polar side of soap. And they're going to mix really well. And off goes the soap that has all your dirt trapped, and you're clean. Good to know how soap works, I suppose, right? So the other thing that we typically use soap and detergent for, right, is when we wash our car, right? You go wash your car, you wet your car down, you get some of that beading to occur. The next thing you typically do is do a little soapy water, right? And when you add soap to water, what it does is, because there's the polar part, it interferes with the hydrogen bonding that happens between the water molecules at the surface. And what that ends up doing is allowing basically your water to spread out, right? So it spreads out. Because of that, it kind of breaks that interaction. You obviously can then pick up any kind of dirt and grime with the non-polar part of soap as you're washing your car. And then the same sort of effect happens like when you wash your hand. At the end of washing your car with the soap and water, you spray it off with water again, right? And the water takes the dirt and the soap off of it. But that's why you sort of see the spreading out sort of occur when you kind of soap up your car and you have kind of soapy water, versus when you just first hit it with the hose. You get all this sort of beading, I guess, depending on how nicely waxed your car is. But even maybe not so waxed car, you'll still see some of that sort of beating and stuff occurring. So this is, again, all has to do with a lot of intermolecular forces that really beating occurring because of the strong intermolecular forces, the water getting in the way of that intermolecular forces between water and water, the soap getting in the way and allowing it to basically spread out. Any questions on that there? So talking a little bit more about the sort of adhesive and cohesive forces that we were talking about before, remember that our cohesive forces, again, that difference between the the attraction between molecule and molecule versus adhesive forces. And what typically happens, though, is another sort of aspect of solutions is, or of liquids, I guess, is what is sometimes referred to as capillary action. And if you ever take like a capillary tube, which is sometimes a tube, a very small tube sometimes, and basically the backside is rounded, usually the front side's open. And if you kind of put it onto a little bit of liquid, it will kind of draw up the liquid into that test tube. And that's because there's the attractive force between the water and the glass, which is going to allow it to basically rise up that little sort of capillary tube in that action. And that is, as I mentioned before, why we do see the typical meniscus forming when we put a liquid into glass container. Again, the attractive forces between the glass and the water, and that example, is stronger than the attractive forces between water and water. And it doesn't always happen in all cases like that. Actually, in mercury, if you've ever seen sort of the meniscus on a mercury, it's actually upside down. And this is sort of where you would take a reading, by the way. And that is because when we're dealing with mercury, the attractive forces between mercury and mercury are stronger than the attractive forces between mercury and the glass. So what ends up happening is the mercury decides, I'm going to be more attracted to myself. And the outside ends up coming sort of in on itself. And we get this sort of reverse meniscus, if you will, because there's a stronger attractive force between the mercury molecules and itself than between, say, the attractive forces between mercury and obviously the glass container. So mercury is kind of an unusual one like that. Again, it has sort of a upwards sort of meniscus, and again, it's because of those attractive forces. Any questions on that there? So then let's talk about another property of liquids, which is what is referred to as vapor pressure. And we talked a little bit about vapor pressure when we were talking about gases the other day. But vapor pressure sure has to deal with obviously vapor. Vapor, again, as we might talk about at the beginning of the gas chapter, is basically the term we refer to substances that are normally in the, say, liquid or solid phase, but can be confirmed or transformed into a gas. So these are typically things, right, that are not normally found in the gas phase. And that's why we talk about vapor pressure. So when a liquid has a tendency to vaporize or go into the gas phase, it is what is referred to as being volatile. It means that it can very easily go from liquid, pop into gas, basically. It increases with temperature. So as you increase the temperature, we would expect more gas to be made in that case. Now, a liquid in an open container will evaporate completely because air will basically kind of push away things. So what do we mean by that? Well, when we talk about sort of evaporation and why things sort of evaporate, let's talk about a couple of different sort of examples. Let's talk about if you had just some liquid on the bench that you dropped, it will eventually evaporate, right? And what happens when we talk about a liquid, just so everybody's clear, at the surface of the liquid, we actually have two things happening at once that you can't necessarily always see, or probably mostly see ever. We actually have liquid molecules that are going to be jumping out and going into the gas phase. We also have slower moving gas molecules that are tired and then go drop back into the liquid phase, right? Basically go through evaporation and condensation. So at the surface of the liquid, you've got this sort of constant evaporation and condensation sort of happening. Guys going out into the gas phase, guys coming back into the liquid phase. So when you have something like a little bit of liquid, maybe a drop or two, or whatever, maybe you spilled on the bench, what you end up having is at some point you've got some evaporation happening, obviously at the surface all around here, right? Since it's kind of spread out, you got all this evaporation occurring pretty much everywhere. Now, in an ideal situation, if nothing else was there, some of those guys that are evaporating would then drop back into the liquid. But there is like air molecules moving around, right? Which are pushing some of these guys that have just evaporated off out of the way, which means they're no longer available to come back into the solution. So then your little puddle gets smaller. This process continues. Air pushes more of it out, gets smaller, gets smaller, gets smaller, gets smaller, until it's basically gone, right? And it has completely sort of evaporated. Same sort of thing happens, right? If you take a liquid and you kind of put it in an open container, right? Same thing's going to happen at the surface. We're going to get some evaporation occurring. We'll also get some condensation occurring, coming back in. But we get the same sort of effect. At some point, some of that air is going to be pushing it around. And what you'll eventually see, right, is your liquid in that container will probably continue to decrease and decrease with time. Probably going to take a lot longer, right, than here, but it will probably kind of do that process over and over again. And again, that's sort of the process of evaporation that's occurring. What causes vapor pressure? Well, it's all those gas molecules that basically come above the liquid. So what happens when we throw the same liquid in a container and we pop a lid on it? Well, we get that evaporation that's going to occur. We also get that condensation that's going to occur. Differences here, for example, definitely in the closed container, those gas molecules have nowhere to go, right? So what we're talking about really is, in terms of vapor pressure, is it's related to obviously the amount of gas molecules that are above the liquid at any given point. By the way, you still have that over here in the open container, right? There's still gas molecules basically hanging out there above the liquid. You're just going to see obviously a much slower, if no evaporation rate, very little happening, and obviously in the closed container, because really they have nowhere to go, right? So whatever was in there when you close the container, they're pretty much trapped in that sort of container and cannot escape. So liquids with very high vapor pressures are said to be volatile. They evaporate really quickly. And the vapor pressure of a liquid at a given temperature is determined on the intermolecular forces. The stronger the intermolecular force, the lower the vapor pressure. So let's talk about why that would be, just to make sure. Remember, in order to create vapor pressure, you need to create gas. And in order to create gas, you need to separate these molecules, which means if my intermolecular force here was really strong, it's going to take a lot of energy to break that apart, which means we're going to end up with less gas molecules above the liquid. Less gas molecules above the liquid means there's less gas molecules causing pressure, and it should result in a lower vapor pressure. Now, if we deal with something like, for example, organic guys, organic guys, those are our nonpolar guys. So say we got a couple of nonpolar guys. They're using those dispersion forces, which is a very weak force, which means doesn't take a lot of energy to do that. It's willing to break apart into the gas pretty quickly. And that means that we would expect a lot more gas above the liquid, and we would have more gas, which would mean more collisions of those gas molecules, which would mean a higher vapor pressure. So if you just think about some of the basic organic sort of compounds, even if you're not familiar with them, but they're basically things like propane, butane, methane. Those are all things you're probably familiar with. Those are all gases. A lot of organic guys are very volatile because they're basically held together by these really weak temporary forces that we talked about, which means even if it is a liquid, it can kind of go into the gas phase very quickly and kind of usually be very volatile, a lot of them, and be able to escape into the gas phase. That's why if you ever dealt with organic compounds, or maybe you're going to take organic chemistry or something like that, I guess I'll put it this way, there's a lot of really bad smelling stuff. And there's a lot of bad smelling stuff because a lot of things are very volatile and can go into the gas phase really quickly. And obviously you can smell them, which sometimes is not a very good thing. It's also why when you're working with organic chemicals or an organic lab, you oftentimes will work inside a fume hood, because a lot of those things can very much and very quickly sort of escape into the fume hood, or escape very easily. So usually you do it inside the fume hood. Trying to think on that video there, but for example, when we typically use or do that experiment that we saw earlier on in the semester, where we did all the halogens and sort of which one's more reactive and stuff like that. Typically when we use those halogens like chlorine, bromine water, iodine water, those things, if you open it, very smelly, right? They smell very much. They could go, even though they're a liquid in that sort of phase, they're very much can sort of vaporize and give off scents very easily, because they're all nonpolar, right? Cl2 is nonpolar, Br2 is nonpolar. They're all doing basically that dispersion forces and not held very tightly. Also, when we did that experiment, we used something like hexane, which is basically 6 carbons and hydrogens, also nonpolar, also using dispersion forces. And if you ever use hexane, you shouldn't smell it, but you will smell it because it does give off a very much odor and stuff like that. And again, because those guys are pretty much working with those really weak sort of forces, that's why, a lot of things are kind of smelly in that sense. They can kind of go into the gas phase really easily. Another sort of effect that we see when we look at sort of a liquid in a closed container is actually the ending volume of your liquid versus where you sort of started. And what I mean by that is when you close the container, pretty much at the start, you're going to have a very high rate of evaporation that's going to happen in this particular container, as we talked about the surface. And as those guys sort of travel upwards, as I mentioned with my drawing, they pretty much got nowhere to go, which means at some point they're going to decide, I guess we'll just go back down, right? And you'll get some condensation starting to occur, right? Starting to make some more water as we lose some water. And at some point, we will get to a point on the right here where the rate of evaporation, it going into the gas phase, will equal the rate of condensation, it going back to the liquid phase. And typically what you'll see, if you really take a pretty good peek at it, is you'll see that volume actually decrease from where it started from. And that's because you very quickly get a lot of evaporation, which is going to bring the liquid volume down. And you're going to get some condensation come back, and at some point it's going to reach equilibrium, and it usually will end up at a volume that's less than sort of where it started. Any questions on that there? So can we sort of figure out some things involving sort of vapor pressure and temperatures and stuff like that? So let's take a look at sort of a calculation where we can kind of look at this. And this is what's sometimes referred to as the Claisen-Clapeyron equation. And we have the natural log of basically the vapor pressure at 2 different temperatures equals our delta H of vaporization. That is our heat of vaporization. I think we talked a little bit about it. R is the enthalpy of vaporization. Again, we don't talk too much about heat in here. These are obviously our vapor pressures at different temperatures. This is actually R, and it's the gas constant, but it's actually the gas constant that involves energy, and it's the 8.314 version of it. And I think we saw that one in a different one. These are our temperatures, and much like anything obviously involving gases, they need to be in Kelvin. So if we look at a a problem like this just to see how it sort of works, and there's the answer. So I guess we'll go and see how we got to that answer. We have the vapor pressure of water at 25 degrees is 23.8 torr. The heat of vaporization of water at 25 degrees is 43.9. Calculate the vapor pressure of water at 65 degrees. So we could do a couple of things here. We obviously have a T1 that is 25 degrees Celsius. We do need to convert it to Kelvin, so might as well just do that right off the bat. We obviously have a P1 that goes with that, which is 23.8 torr. We have a T2, which is 65 degrees Celsius, which we also, again, would want to convert to Kelvin. And if I do that and find where I threw my calculator, there we go. We got 65 plus a T73, looks like a 338 happening. And what else we got there? We also have the delta H of vaporization for water at that, which is 43.9 kilojoules per mole. So we could use the equation that we just saw, which again is the natural log of our vapor pressure at the first temperature divided by our vapor pressure at the second temperature is equal to our delta H of vaporization divided by R, 1 over our second temperature minus 1 over our initial temperature. So we could actually put all our numbers in here. So natural log of our first vapor pressure, which was 23.8, over our second vapor pressure, which is what we're looking for, equals our delta H, which is 43.9 times 1,000. So you may be wondering why I'm multiplying this by 1,000. I am doing that because my delta H is in kilojoules. And if you remember, R, which goes on the bottom of it, is actually in joules. So you got sort of a unit situation happening here. You got to either convert everybody to kilojoules or convert everybody to joules. So I'm just choosing to convert to joules so I don't have to convert the bottom number. So I'm just going to leave that guy like it is. You could definitely convert everybody to kilojoules, should come out okay. We're going to do 1 over our second temperature there, which is 338, minus 1 over our initial temperature, which is 298. Any questions on that so far? I'm going to clean up the right-hand side there. So I'm going to take 43.9 times 1,000 divided by 8.314. It's going to give me something like 5280.25. And clean up the parentheses. 1 divided by 338 minus 1 divided by 298. Going to give me negative, it looks like 0.000397125. If I did that correctly there, just to make sure. And minus 1 divided by 298. All right, then multiplying those guys together gives me 5280.25. Gives me the natural log. By the way, this still equals natural log of 23.8 over P. Gives me the natural log of 23.8 over my vapor pressure will equal minus 2.09691. To get rid of the natural log, we actually take the E of both sides. So if you look on your calculator, you see that. When you take the E of the left-hand side, the natural log just goes away. You take the E of this. So coming up on top gives me 23.8 times my pressure will equal E, and you do want to keep the negative there, 2.09 change, gets me 0.1228. Multiplying the P to the other side, dividing by the 0.1228. Let's spit that out. There we go. Those guys are going to cancel, and that is going to yield us a 193.7. And it would be the same units as the other guy, which is torr. And again, rounded to 194 in that particular case. Any questions on any of those steps along the way? So what do we see here when we sort of look at this? We see that the temperature increases. And what do we see about the vapor pressure? The vapor pressure also went up. That does make sense if you think about just the basic idea of vapor pressure is basically our gas molecules above our liquid, which means when I increase the temperature of this, I should expect a lot more guys in the liquid phase to have a lot more energy and be able to escape. So I should be getting a lot more guys able to escape above the liquid into the gas phase. And because there would be a lot more gas molecules above that liquid, we would expect a lot more collisions and obviously a lot more pressure associated with it. Any questions on that there? Okay. So I think it's a good place to stop, I think. Any questions on anything we talked about today? Okay, so